Welcome to Module 7, and what we have now is topic 7.3, where we're going to discuss some examples. We talked about model-based testing, and then we looked at the finite state machines and even the other ways of modeling and how modeling can help us come up with good test cases. It's a design way of doing things. A design comes into reality first, a model, and then we get into designing the test cases. In fact, it would also be a great effort to understand the system breadth-wise and even depth-wise. So let's start off with a very simple example. We start off with a stack, a simple stack that we looked at even in the previous topic. How is a stack going to help us understand, and we'll build the whole piece right from simple state machine to how models can help us. So take a moment, look at the entire diagram, the state machine that I have drawn, and you should be able to find out issues with it. I'm sure there are issues with it. There is at least one that is clearly a problem that can be observed if you observe it closely. Okay, I hope you have been able to find that out. So here lies the first one. There is a pop over there, so we'll just put a push. A pop when it is empty. So we've got three states: empty, partial, and full. And we are looking at a pop here or a push here does not change the state, or a push and a pop remains in that state provided we are not on the first or the last element. So if I have 10 elements that can be stacked up, then we know how long it would stay in the partial state. Let's take this problem further, because it doesn't look like that the amount of notation that we have is enough. And before that, let's also get to the enormous number of states that we can get to. Specifically because there is one piece that will add on to the notion of bringing a limit, is that I could keep on doing the push-pop cycle over here forever. I could do a push and a pop, push and a pop. So ultimately we see that there could be a state explosion problem. If I create, one is the push pop piece, I'm moving from one state to the other. The other is that I'm moving from one state to the other state, and every state is depicted as if I have got one more element in the stack. So those many number of states. Thus, if I have a growing stack, I would always have growing number of states. Now this, just being academic, from that interest as well, one should know that there should be a limit for some of the number of states that we looked at. And if you recollect, we were looking at the fault model as well. So we do not wish to have erroneous states or states which are just extra. So here we look at it from a perspective that we may have a state explosion problem. To depict the condition and the action, that's our prime focus, we bring on an extended finite state machine. Here we explain it in the most simplified form, solely because this is not a design class. We are looking at utilization of this to get to writing test cases. So let's utilize what we have at hand and then get to those test cases. But utilization in a form which is simpler and fits the purpose. So what we have here is an EFSM, and then it does this job of providing a condition and an action between states. So the way we start with is this. The system is in S 1, an event occurs. An event occurs, the condition evaluates to true. So we have condition that evaluates to true. So that's the third step. Transition from S1 and S2 takes place and the action is performed. So these are the steps that are followed for a particular state machine, extended finite state machine. Now imagine, would such a notation help our stack be represented a little better? Yes, it will. Take a close look at the entire representation and see how many problems do you find, or if there is a problem that you find. What we have, max number of elements is 10. And now we have transitions that happen along with the condition and also the action that takes place. So what we have is again empty, partial and full, modeled in a manner that you would have the entire state transitions happen. It takes care of the three major states and also provides more information with respect to condition and action. So let's take this forward and look at if we have to see stack as a component. Now we have to test this stack as a component. So we have got operations or methods that come to us, which is push and pop. And now we are going to do state-based testing. So what does it mean to us when we are doing state-based testing? So we start putting a criteria onto the state-based testing. Every state in the model should be visited at least once. Every transition should be traversed at least once, and traverse every path in the model at least once. Now you can see we have got state, transition and path. So we have got state, so there are three states marked with red. How many transitions do we have? Let's mark the transitions with green. So I'm going to mark transitions with green. This is 1, 2, 3, 4, 5, 6, 7, 8. 8 transitions that we came up with. And how many paths do we have? That is something we got to look at. I may have numerous paths because now between state, empty and partial, I can keep on doing 2 and 3 numerous amount of times. Or I can do 6 and 7 numerous amount of time. Or I can keep on doing this loop or this loop numerous amount of time. So we also need to be prudent in what kind of paths we select. But the strategy, I hope, is very clear. We could now represent the entire diagram as a graph, which is, this is one node, got another node here, another node here, and then so I'm just making sure that we draw all the transitions here. So I've got node A, node B, node C. And then I looked at transitions 1, 2, 3, 4, 5, 6, 7, 8. If I now look at it as a graph, state testing becomes node, traverse every node, transition becomes every edge, and path becomes every path. That is, let's take an example of a path. Path would be that I do 1, then I would like to do 2, then I would like to do 3. So I could do one path 1, 2 and 3, which would mean, let me mark it with another color. I first do the 1, then I do the 2, then I do the 3. So 1, 2, 3 is how I can traverse a path, and I would have tested 2 states. This particular path includes certain functionality. Let's take this further and see how I could arrive at the state coverage. So these become my test cases. Test case 1 would be to push, so I move to partial state. I perform push operations and then I get to the full state. So this would make state coverage satisfied. So that's what I get to. Next is transition. So in making it full, we created certain amount of transitions already. So if I start looking at the 11th push, will not be able to make the 11th push, but I would have covered a transition. And then you start looking at popping and coming back again so as to cover the rest of the transitions. As we move on, let's get to constrained path testing, which is equivalent to modified path testing. And this modified path testing will come back to us even when we are looking at the code-based testing pieces. And you may recollect the concepts from there. So we are talking about traversing every path. Now every path that we are looking at is also for another problem. You would actually see that in this case, every path, right from start to exit, we definitely need to know the limits, especially of these loops that we could create. So I could have this loop and I could keep on going into the system. For example, I could keep on going into the system in this manner by not really coming out of the system. So in that case, we define a particular constraint. What would that constraint be? That I'm going to traverse, say once, for example. So I allow certain thing to happen no more than one time. Like in case of our ATM, we do not allow wrong pin to go more than 3 times. In fact, we not only constrain it, by behavior, we block the card, or we actually let the user know that he has entered it 3 times, and depending on the policy of the particular bank, we are going to take the necessary action. So from state, transition and path, and we also now start putting the constrained path, which allows us to get to a very clear-cut testing for every state. I hope now right from model to getting the test cases is clear. And in our next topic, we should be able to take a detailed example with a little more complex example or a complex case. So here constraint path, if we really see, we have defined constraint path, and each of the T1 to T11 form the paths that would be traversed. We start looking at test cases that will make it happen. I would rather say take a pause and traverse each one of them, but I'll do that probably for a couple of them for you. I'll do that for 2 of them for you. So let's take T4. T4 is T1, T2, T3. So start T1, T2, take T3, T6, T9 and T10. Let us look at T11. Look at transition 11. We look at T1, T5, T8, T9, T2, and then comes exit. So you look at the variations that could be got when we are looking at a path. Also, depending on how the state machine is designed, every path may not be even reachable in the sequence that we design as if it were a graph. And that is where understanding of what that state machine is will be important to apply such a path testing rule. So, three things what we did as a part of state-based testing. We also need to consider that there may be non-executable elements. In a particular sequence, certain things become non-executable in a particular state. Like when we have got stack to be full, a further push is not possible. And of course, when the stack is full, you cannot bring it to empty just by one operation. You got to go through the partial as a state. So there will be certain elements which will be very context driven or state driven. So with this example, which is a simple example, we would have gotten all the elements that we need for us to tackle a little more complex example. And that's what we look at in our next topic, where we are dealing with a small case. Thank you.